Alright, today we're going to look at key features of quadratic functions, and this is part 1. We're going to look at 4 key features from analyzing our graphs. So look at your vocabulary chart. You have 4 columns. The first column has your key feature with the proper vocabulary, and then the second column has the definition, and we'll write some helpful hints in there to help us remember exactly what we're looking for. And your third and fourth column together give you illustrations that we'll be able to practice putting these key features and definitions to work with proper mathematical notation. So the first graph there in column 3, it's the same. All the way down column 3, it's the same graph. We're just going to be looking at different features each time for each row. But that graph is a normal width and it opens up. Whereas your graph that you have in column 4 is a little skinnier than normal, and it opens down. So those two graphs should give us some variety so we can see how our key features differ as our quadratic function transforms. So let's go ahead and start with maximum or minimum. Maximum or minimum is the very highest or lowest point on the graph. And so we know the highest or lowest point as the vertex. And so we're just increasing our vocabulary and really determining where that vertex is located. Is it the highest point or the lowest point? So let's check our first graph. This graph opens up, and so our vertex is right here at the point 0, -4. Now the question is that vertex the highest or the lowest? Is that our highest or lowest point on the graph? So it is the lowest since we're opening up. We continue up forever, but as low as we go is 0, -4. So if that's the lowest point, then that's going to be a minimum. And then let's also note where that minimum is located. It is at the point 0, -4. So give me the coordinate of the vertex. X, Y, ordered pair. Okay, look at your last graph. Spying our vertex right up here, tip top, at 1, 2. And so that is the very highest point, so we call that a maximum. And that maximum is located at the point 1, 2. Okay, so vertex is something we're very familiar with from our work already. We are just defining it a little more specifically with this key feature as a max or a min. So my question for you is, you can tell that from your graph very easily. You can spy that, no problem. Can you tell me if you have a maximum or a minimum from your equation? Now, I know you can find your vertex because it's the point HK. We are pros at that. That's not what I'm asking. I want to know if that HK vertex is a max or a min. So think about it. When your parabola opened up, what did we have? A minimum. When your parabola opened down, what did we have? A maximum. And that's always going to be the case. So we know if our parabola opens up or down based off of our A value. A tells us if our parabola is going to open up or down, depending on if it is positive or negative. So if our A is positive and we're opening up, that means we have a minimum. And if our parabola opens down because our A is negative, that means our vertex is going to be a maximum. So we could tell just by looking at our equation because we know whether we open up or down. Okay, good. Let's look at our second feature. Our second feature is looking for zeros, roots, x-intercepts, or solutions. Gotta love the English language and math. We have 4 different terms that for the most part are looking for the same thing. It all means the same thing. You're probably most familiar with x-intercepts. That's something we've been working on all year, and that is probably the term that is the most sensible to you. Now, the way you give your zeros, roots, x-intercepts, or solutions, like the notation itself, could vary. We're accustomed to solutions. We solve equations. We haven't solved quadratic equations yet, but we are used to the word solutions for when we're solving an equation and we get an answer, x equals whatever, right? If we're talking x-intercepts, we know that's a point. We've got to list it as x, y ordered pairs. Same thing for roots. That's very much similar to your solutions as well. And then zeros is just a fancy word for x-intercepts. Think about how x-intercepts are going to be x and some number, right? Some number for x, and then your y-coordinate is always going to be 0 if we're on the x-axis. And so that's where that term comes from. Okay, now if you look at your definition, it says f of x equals 0. Remember, f of x is our fancy notation to tell us that we are dealing with a function. For every input, there is exactly one output that corresponds to it. And so we know we have a function, our graph. We're going to look at our graph and it passes the vertical line test. It just tells us that y depends on x, and there is a unique relationship between those two variables. So f of x is the exact same as y. So this just as easily could say y equals 0. Right? Go back to your ordered pair. Y equals 0, solve for x. Find your x-intercepts. So if y equals 0, what is x? Okay, let's see if we can spy our x-intercepts in this first graph. Where is our graph crossing the x-axis? Our parabola hits the x-axis at two spots, right here at -2, 0, and also on the positive x-axis at 2, 0. Okay, so let's list those, -2, 0, and 2, 0. Remember, we're looking for where f of x equals 0. So right there, y equals 0, x is -2. Y equals 0, x is +2. We have two solutions. Our graph crosses the x-axis twice. Zeros, roots, x-intercepts, solutions. Okay, for your last graph, we have two x-intercepts as well at 0, 0, and 2, 0. Okay, so one thing that you might want to note is that these first two features are both points. If we are looking for our zeros, you're giving me an ordered pair, x, y ordered pair. If you are talking about your max or min, that's also a point, an x, y ordered pair. So those first two are actual points on your graph. Now, for our next two, you might want some highlighters or some colored pencils to kind of help you visualize this. Okay, let's go on to domain, feature number 3. Domain we've worked with before in Unit 1 when we were looking at a relation, trying to determine if it was a function or not. Looking at that set of ordered pairs, we may have just had a list. We could have had a mapping with arrows connecting x to y. We did look at graphs. We also looked at table of values. So domain is something we're familiar with. We know that domain is all of our x values. So if we're talking x values, my x-axis goes from left to right. And so I'm looking for where my graph is all the way to the left and all the way to the right. So how far left does our first graph go? Now, lots of people want to tell me that it's at -3 because they see that it stops right here at -3 on the x, right? They're looking right here. But that's not true. We know that we could step 4 units to the left from our vertex. And if we are stepping 4 units from the left of our vertex, and get to my vertex, and we're going over 1, 2, 3, 4, how far up would I have to go? This is a normal width, so I'd have to go up 16 units. So yes, that's way off my chart, but my graph is still there. If I went to the left 5, I'd go up 25 units. If I went to the left 10, I'd go up 100 units, right? Because we're dealing with our square function. Every step we take left and right, we move up the square of that from our vertex. And so we know that our graph really does keep building to the left and up and to the right and up forever. So how far left does our graph go? All the way to the left, forever to the left. How far to the right does it go? Forever to the right. All the way, forever and ever and ever. What do we call that if we're going forever? Yes, infinity. So if we're going left forever, infinity and beyond, right? Keeps on going. So if we're going left forever, then that's negative infinity. And if we're going right forever, that's positive infinity. Okay, now, when we are making this notation, we know that we're looking for how far to the left does our graph go and how far to the right does our graph go. Left to right. Now, when we're giving our notation, we don't write the word to. We put a comma instead. And then, since it's infinity and it keeps going forever, we can't stop that, so we just leave open parentheses around our interval from left to right. So how far left did we go? We went from, how far left? From negative infinity, and then how far right? All the way to positive infinity. Good. Now let's see what happens when our graph reflects over the x-axis. This graph is opening down. What happens to our domain? How far left is our graph? We know that this is going to continue down and left forever, and this is going to continue down and right forever. So how far left? That's right, negative infinity. And how far right? Yes, positive infinity. Good. So give me the interval from where to where do we have x values on this graph? How far left does it go? Negative infinity. How far right does it go? Positive infinity. Okay, so it's important to notice that this domain is given as an interval. It is not an xy ordered pair. We're not talking about a point. Now, it looks like an xy ordered pair, except that we've got these weird infinities instead of numbers, right? It looks like that just because of the parentheses and the comma, but it's an interval telling you from here to there. From the left to the right, how far do I see my graph? Okay, let's try range. Range is all of your y values. So we're talking high and low, right? We want to know how low does our graph go and how high does our graph go. So from low to high, that's what we're looking at. So let's take this first graph. How low does this graph go? The very lowest on the y-axis is -4. There's not another point on my curve lower than that because that's my minimum at the vertex. And then how high does my graph go? I know that we continue to the left and up, to the right and up forever. It's going to go up and up and up as high as can be. And how high is that when it's forever? That's positive infinity because we're moving up. Okay, so again, our notation is going to be from low to high, but instead of 2, we're going to use a comma. And so let's look. What is our very lowest? Our very lowest is -4. And our very highest y value, right, we don't use the word 2, we use a comma, from -4 all the way to infinity. Now, we said when we were working with our domain that we are going to never be able to stop infinity. We can't stop that. It keeps going forever, so we use our open parenthesis. But -4 is the lowest. It stops. That is a point on our graph, and that is the very lowest point, and there's nothing lower than that. It doesn't keep on going. So we don't use open parentheses if it actually does stop. And so it stops at -4, and we're going to show that by using our square bracket. So you might use parentheses or square brackets on these ends for your range as opposed to your domain. Look back at your domain. It kept going left and right. Your parabola stretches all the way left and all the way right forever, no matter what, whether it opens up or down. But on your range, when you're looking at y values, there is a peak. And so that's why we have those square brackets coming into play. Okay, let's try our range for our last graph. We want to look at our very highest and our very lowest. And we always go low to high. Our notation is always from smallest to largest. So let's go low first. How low do we go? I see that I've got the ends of my graph here, and so I need to look at those as arrows. They keep on going out and down forever. And so what do we call forever? If we're going down forever, then that is heading to infinity. Yes, but it's down. So down means negative infinity. Okay, and how high does our graph go? Oh, I'm going to run out of space here, aren't I? Let me try this. Negative infinity, all the way down. Okay, now how high does our graph go? Yep, we're looking for that vertex because we know that's going to be our maximum since we're opening down. And that vertex is happening right here at a y value of 2. Nothing goes above that. So our very highest y value is 2. Okay, so low to high. Lowest is negative infinity, 2. We don't use the word 2, we use our comma. And then from here to there, what's the very highest? 2. Now, can we stop infinity? No, it goes forever, so open parenthesis. Does our graph actually stop at 2? Yes, that's the highest y value, so square bracket. It is a point on our graph. Negative infinity to 2. Okay, now this is very similar to domain because you are giving me an interval from here to there, from low to high. Since we're talking about y values, y-axis, y to the sky, so we're going up and down, right? Starting from smallest, the low, to the biggest, the high.